So then we fasten our seat belts and we go to gravity. And here I think it's a huge topic and it's difficult to pay kind of justice, give justice to it in just 15 minutes. But of course we have seen in some sense, and you have seen that argument before. Now, we have two wonderful theories in nature. We have quantum mechanics, quantum field theory, particle physics describing the very small, general relativity, the theory of space and time describing the very large. And we feel there's only one nature, so they should come together. So how do these two things come together? Well, there are practical, experimental parts to that. We'll hear much more about that, I hope, this afternoon when cosmology will be center stage. But let's also just look at the conceptual level. So we need something which we call quantum gravity, which is kind of almost by definition anything that glues the two ends together. Now, Brian very elegantly explained to you what Einstein's theory of general relativity was, and I will just summarize to you, it's just a concept. If you put anything in space-time reacts to it. You know, the curvature of space and time becomes a dynamical variable. It literally curves around in a very specific way described by very elegant formulas using the geometry of curved space. And then it's important to realize, by the way, that Einstein was extremely lucky that the formulas he needed and the whole formalism actually was developed 50 years earlier by a mathematician, particularly by the mathematician Bernard Riemann, who took him by himself, without any probing, the intellectual leap of thinking of higher dimensional spaces and thinking of space being curved, not being curved inside something else, but just curved by and through itself. So Einstein was extremely lucky. He had all the mathematics, basically he had his toolbox already filled. And he's in a very different position, I think, than we are right now, where math and physics are really working you know, simultaneously at this, and with each other. And of course, as we saw, it's the movement as going as straight as possible in that curved space-time is the way we understand gravity. Now, you should realize that this really looks like a completely different picture than I told you what is the way we think about the other forces. Because the other forces we think about as an interchange of particles. It's basically this kind of tennis matches where you have two electrons and they hit the tennis ball being the photon left and right, and that's the way they are interacting. This is very different. These are ripples in space-time. And in fact, you can take the same, at least mental exercise. They say, well, think about these ripples in space-time and think of them, in particular, there are waves. And we have seen these waves indirectly in measurements. So not ripples in a field in space-time, but ripples in space-time itself. And you can think, well, dial down the amount of energy you put in. At some point, you will get little quanta, little bits of energy. And so you will have a particle. And in fact, you can compute what the properties of the particle are. It's again a massless particle, which means it can travel as far as it wants. It gives the 1/r² law. But to capture fully Einstein's relativity theory, it actually has to be a particle of spin 2, not of spin 1. So it's different from the photon. And in fact, we also know that there is room for a spin 2 particle in nature, but you can only have one. And so that should be gravity. So we know there. And if you're a particle physicist, let's do an experiment with two gravitons. It would be very difficult to do here on planet Earth. But you could think of having two gravitons scattering. And what are the properties? And you will find what is the strength by which gravity interacts with itself. And you find the number is actually Newton's constant. And a particle physicist would look at Newton's constant as 1/mass². In fact, in very natural units, the so-called Planck units, which Planck found actually in the year 1900, the same year when he discovered his Planck's constant, he knew that if you had Planck's constant, h bar, and the speed of light, c, and Newton's constant, g Newton, and you would have a kind of set of natural units. You would never have to use any units at all. No inches or meters or miles or kilometers, no confusing at all. There are natural units in nature. They are natural in the most literal sense of the word. And it would be a length scale, which is the Planck length, 10 to the minus 35 meters, which is roughly 10 to the 20 times smaller than the scales that are relevant for the standard model. And it would be similar an energy scale, which would be 10 to the 19 GeV. And just to remind you, the LHC is at roughly 10 to the third, so 1,000 GeV, or a TeV. So way, 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 way beyond anything that we can measure. And there are various ways to think about this Planck length. I mean, one way to think about it is often said, this incredible effect of gravity that is so weak. And this is something that you probably not all realize at this moment, but it's something you can easily demonstrate. And so by comparing two forces, so if you compare the force among particles coming from, for instance, electromagnetism, or even more pronounced would be the strong force, if you compare that to the gravitational interaction between particles, the gravitational interaction is absolutely totally negligible, because in some sense, the one way to think about the gravitational force is that the charge for the gravitational force is the mass, and the mass should be done in Planck units, so that's actually incredibly small. And so if you were to think about how heavy particles should be, so that actually particle theorists, particle experimentalists would start to worry about gravity, then the elementary particles would roughly be the weight of a bacterium. And so there's this incredible factor of 10 to the 19th, that's the difference between the Planck mass and the usual masses that you have in particle physics. So another way we think about it is that, as I said, quantum mechanics give ripples in everything, in particular in fields. That's kind of this Casimir effect. So it should also ripple space-time itself. So there should be kind of a natural unit where space-time itself becomes kind of, we have used the word quantum foam for this, but it's just kind of a way of speaking, where space-time itself doesn't make sense. Another way to think about it, perhaps space-time is a little bit like this picture. If I zoom in and in, at some point you get the individual pixels. And there would be kind of atoms of space and time itself. And the size of the atom would be the Planck length. Incredibly small length scale. Now, so it's important to kind of see this in perspective. So here I just in one slide gave you both the largest size that we know, it is the size of our physical universe, and the smaller size. And quite conveniently, if you take the geometric mean, you find roughly the size of a biological cell. So that picture, the 60 order of magnitudes, that's in some sense one of the biggest questions we have in nature. It's the question, why is the universe so big? I think we'll address this afternoon. But there's another way to look at this picture, because people have endlessly speculated about the infinitesimal small and the infinite large. And they're kind of both out. Now, modern physics says, well, there's a largest scale that we want to understand. There's a smallest scale. They differ by a factor 10 to the 60, which is an amazingly large number. But it's a finite number. So at least we have phrased a good question. Explain to me where this number is coming from. And both the infinitesimally small and the infinite large do not really play a role in our physical theories, which is in some sense a relief. There are many, many philosophical and technical questions related to this. But if you're a particle physicist, there's another way to think about it. So we say, well, there are these self-interactions of the graviton that go with basically the equivalent of the strength of the force, which goes to 1 over the mass of the Planck. And there is an effect to this I won't explain here. But the fact that your interaction has the dimension of 1 over mass squared, it's both a serious problem and it suggests a solution. It's a serious problem, but the moment you start to compute these virtual particles, the things that can happen out of nowhere, if you have more and more of these particles, then actually the effect will be stronger and stronger. So I'm basically telling you that this fact makes your theory mathematically inconsistent. Now, this is not really a reason to give up, because we have at this point before in the history of physics. For instance, if you look at the theory of radioactive decay, the radioactive decay of particles, so for instance, you can have a proton decaying into a neutron. This is the physical effect. There was a wonderful theory for this by Fermi in the 1930s. And it had the same effect. It had a strength which was proportional to 1 over a mass squared. And that mass was 300 GeV, which actually is the mass, which is really the mass associated to the Standard Model. That theory, again, was inconsistent. But we have improved on this. In fact, the Standard Model has a different description of this and said radioactive decay is not just this kind of point interaction. In fact, it's the mediation of a particle that goes in between. In fact, it's one of these force-carrying particles. In this case, a force-carrying particle of the weak force. It's the SU2 part of our Standard Model. And in fact, that's a particle with a mass. And the fact that its mass is around that order tells you why the effect goes like with 1 over the mass squared, because that's just an explanation. So the previous picture, this picture was kind of a caricature. You have to zoom in, and then you see actually this kind of this intermediate thing going there. And that explains it, and then the whole thing becomes well-behaved. And you have this wonderful tool that you can compute many, many, many orders of perturbation theory, and it does make sense. So you can argue perhaps there should be something similar in graviton-graviton scattering. There's like an intermediate W boson, the equivalent for that, which is something which have typically a mass scale which comes with the Planck mass. And so roughly that's one way to motivate any theory of quantum gravity, particularly something like string theory, by saying, well, there are lots of other particles. The particles, you don't see them because they're very heavy, but actually they smooth out the inconsistencies and make the theory well behaved. Well, string theory, which is the idea that particles, even most fundamental particles, are not really zero-dimensional points, infinitesimally small points, but are little extended objects that can vibrate, has many, many consequences. So it's, of course, a good topic to have a 10-hour lecture course on. But the best simple thing to know, if you look at a string, it can oscillate, it can vibrate, just as any other string does. Actually, according to the same mathematics as the mathematics you learn of a simple violin string. And the lowest order of vibration actually produces a spin 2 particle. So you can think of a string as a dressed-up graviton. It's a graviton together with many other particles that make the things behave well. And in fact, if your string moving through space-time, it not gives these spaghetti strands, not this one-dimensional world lines, the thing we call the world sheet, a two-dimensional surface. And you can look at the interactions of these strings, and just at the pictorial level, you see that this picture looks much more smooth than the pictures that you draw in particle physics, where any particle physics process, you have two particles hitting head-on. So these are infinitesimal point-like objects hitting head-on and producing a third particle. Here we have these kind of floppy strings moving and gluing together, making these beautiful two-dimensional surfaces. And the smoothness of these diagrams, particularly if you have loop diagrams, translate into a mathematically consistent theory. So the great thing is of string theory about all the other issues it has, it produces for you a mathematically consistent way to describe gravity, to describe quantum gravity, to describe quantum gravitons. And that's already a terrific thing because that's at this point also the only way we have managed to do so. Now there are many consequences of string theory. I just want to mention one and then stop. And the one thing is actually we talked about extra dimensions. So just going through the list, Einstein added time as an extra dimension. And then we thought that supersymmetry might add these kind of funny infinitesimal anti-commuting dimensions. But what about a real physical dimension? And this actually something was explored very early after Einstein's discovery of relativity theory. In fact, it's called Kaluza-Klein theory because it was happened in the 1920s. And a great story because the paper was actually given to Einstein to referee. And I think he sat on it for 3 years, not reacting, and just because he was so triggered by the idea. And I think, I like this. This was his idea of unification. And one of the effects is if you have a particle that can move in the fifth dimension, particularly if the fifth dimension is a little circle that can go around, there's a lovely mathematics. If you think of a particle going around in a circle, under the laws of quantum mechanics, it cannot go at any speed. It's kind of its speed is quantized. Basically, it can go once or twice or 3 times. And if you see what that means in the rest of the universe, in the uncompactified 3+1 dimensions, it turns out that you're describing a particle with an electric charge. A charge that's 1, 2, or 3 times the elementary unit of electric charge, which would be the single quantum going around the circle. And if you see what happens, so there's this very simple formula that if you take gravity in 5 dimensions, 5 space-time dimensions, and reduce it down to 4 dimensions, you get gravity together with electromagnetism, kind of for free. And you understand why charge is quantized, you get the nice properties. It all was lovely. In fact, looks wonderful. There's only one big but, which is, and I can all of you challenge to do the calculation. It's a very simple calculation. Basically, we've done it already. Just compute what is the size of this extra dimension. Given the fact that you want to describe electromagnetism, you want to describe the charge of the electron. We know the charge of the electron, so you can just compute what the size of the extra dimension is. And there you find kind of a difficulty, because you find that the size of the extra dimension is of the order of the Planck length. So that means this idea, this great idea of extra dimensions, can only work if you're comfortable enough to talk about quantum gravity. Now, Einstein, of course, kind of was really fighting tooth and nail kind of many of the consequences of quantum mechanics, only making it stronger and stronger. Now, every attack he had, there was a wonderful answer, and it became even better. But it's a very poetic thought that his ideas of unifying the forces through geometry and extra dimensions kind of only do make sense if you embrace the ideas of quantum mechanics. And in fact, in string theory, and Brian is really the person to talk about this, being an expert in this himself, because we have a much more convoluted situation where we not have one extra space-time dimension, but depending on particular physical model, up to 6 or 7 extra dimensions that can each of them be curved in a very complicated way. But they do unify particle physics, I would say in the spirit of Einstein, in the sense that the shape of the internal dimension, I already described that just if you add an extra circle, the length of the circle will translate into the charge of the electron and the properties of electromagnetism. But in the same way, if you introduce more of these extra dimensions, you can what we call geometrical engineer physics in the remaining 3 + 1 space-time dimensions. So particle physicists become kind of higher dimensional sculptures. They have to think of these spaces in order to reproduce the thing that was on the t-shirt on the right-hand side, which was the laws of physics. Now, of course, there's again a big why question, which is why that particular space dimension? And as I promised, any why question, I would move ahead to the next speaker. I think we'll see this consistently throughout the day. Because on the one hand, it's beautiful. I mean, this is my final slide. I think Einstein's fundamental idea of unification is saying, well, I took this bizarre phenomena of gravity and explained it almost away by using the geometry of space and time. That idea actually is still valid and alive. And I think in string theory and many other theories of unification, actually that's what we do. We think actually in terms of using geometrical tools and geometrical language to capture some of these questions. But I think actually even Einstein would argue that, yes, indeed, he has a beautiful theory. He liked general relativity very much. But it's a theory that allows for many, many solutions. So this question, why that particular space? Why is it curved like that? I think that still has to rest. And I think that actually is, I think, a perfect point to end this talk. Thank you very much.